Hello everyone, welcome to Azure Cosmos DB Conference 2025. My name is Srinivas Reddy Mosali and I'm a Senior Consultant Systems Engineer at Visa. In today's session, we'll explore how Azure Cosmos DB helps optimize resources for enterprise AI workloads. We will discuss how it supports AI models, improves efficiency, and ensures seamless performance at scale. So these are the key topics we will go through in this particular session. First, we will look at Azure Cosmos DB in AI architecture. In this section, we will discuss on Azure Cosmos DB, how it supports AI with feature storage, metadata management, fast inference, and feedback collections. Next, in the advanced optimization techniques, we will go through some of the best practices for efficient data partitioning and resource management. In technical demonstration, I will quickly give an example on how Azure Cosmos DB handles real-time AI pipelines. Going further, in custom monitoring dashboards, we will discuss how to track and manage AI workloads effectively. In multi-region deployment architecture, we will go through how Cosmos DB ensures global availability is done. And finally, in cost optimization, I will discuss on ways to reduce costs while maintaining high performance. So let's start with the role of Cosmos DB in AI architecture. So AI systems need fast, reliable, and scalable databases. So Azure Cosmos DB plays a key role in four critical areas as mentioned here. First, we will discuss on feature vector storage. AI models use feature vectors and numerical data points for making predictions. So storing them efficiently ensures fast and accurate AI processing. Cosmos DB provides low latency, high speed storage, making AI models respond quickly. And its global distribution allows AI applications to access data instantly and from anywhere. Secondly, we will discuss about metadata orchestration. So AI models also rely on metadata like training logs, parameters, and configurations. So managing this efficiently ensures smooth AI workflow happens. So Cosmos DB supports flexible schemas, meaning it can adapt as AI models evolve. So having this high availability ensures metadata is always accessible even at scale. So having multi-region replication keeps data synchronized across different locations. So uh, let's also deal next we will also go through high throughput inference serving. So once the AI model is trained, we need to serve the predictions in real time, right? So Cosmos DB ensures the fast and efficient AI interference serving is happening. So it delivers with multi-second latency. So meaning AI predictions happen instantly without any delay. And then Cosmos DB can also auto scale based on demand. So which ensures uninterrupted performance all the time. It can also work with multiple APIs, making Cosmos DB easy to integrate with AI systems. Then we have scalable feedback collection systems. Here, the AI models improve when they learn from feedback. So Cosmos DB helps collect, store, and then analyze the real-time user interactions to make the AI smarter. These systems take large-scale data from users, IoT devices, and then applications. So it enables the real-time analytics and then helping the AI teams refine more models more continuously. It also has a low latency global access, which ensures the feedback is captured quickly. Moving on, so let's talk about how we can optimize the AI workloads using the advanced techniques in Cosmos DB. As AI applications grow in complexity, we need a database that can handle fast data access, efficient partitioning, and dynamic scaling. So Azure Cosmos DB provides these three key optimization techniques to achieve this. So let's start with specialized container design patterns. So AI models process different types of data, and organizing this data efficiently is crucial for any kind of performance. So in Cosmos DB, we can use containers to store embeddings, feature collections, and metadata archives and feedback streams. So in embedding storage, AI-generated numerical representations are used to search and recommendations. In feature collections, structured data is used in AI models for predictions and training. In metadata archives, training parameters and experimental results are used for tracking all the models. And in the feedback stream, user interactions and real-time feedback helps model to improve the model over time. Next, we have a partitioning strategies for ML machine learning data access. So the partitioning is essential because AI applications process huge amounts of data, and then partitioning can be done in different ways. Like by using a logical partitioning, grouping can be done for user data, model type, or a region for fast lookup. And then range-based partitioning is ideal for time series data like training logs and model updates. Uh, Selecting the AI optimized partition keys ensures that frequently accessed data stays in the same partition to reduce the query latency. So, for example, if you take an example of a fraud detection system, partitioning partitions transaction by customer ID. So, when a new transaction occurs, the AI model can instantly check previous transactions and then detect any errors in the real time. Moving forward, let's talk about the dynamic RU, the request unit allocation strategy. Since AI workloads are unpredictable, sometimes they require high throughput for real-time inference, and at other times less computing power. So Cosmos DB solves this by auto-scaling the resource request units, which adjust the resources dynamically based on demand. It also does the cost-efficient scaling, preventing over-provisioning and saving costs, or by loading load-based distributions, like ensuring like high priority AI tasks always get enough resources. So these are the different strategies which we can use to implement in our workloads. So take an example of an AI chatbot system, which experiences like traffic spikes during peak hours, right? So dynamic resource RUs allocations ensures that even during the high traffic, users get quick responses without any delays. So by leveraging these techniques, we can build high performance, scalable AI solutions that can handle massive data loads. So let's walk through this demo on change feed based feature pipelines and how this pipeline works step by step, right? So first, we start by enabling the change feed in Cosmos DB. Think of this like turning on notifications. Like every time there's a new event or an update happens, the Cosmos DB automatically captures that change. We don't need to keep checking for those updates. The feed pushes the changes to us automatically as they happen. So the partition key, for example, the entity ID and the event type, like helps to keep the updates well organized and efficient to process. Next, we set up an Azure function that listens to these change notifications. So you can think uh, this as an automatic worker that springs into action whenever a new data arrives, right? So as soon as it detects a change, it grabs the new document and loops through each one of them to process them. So once we have the raw data, the next step is to transform it into something machine learning models can actually use. So this is where we calculate the features, maybe the scores, averages, and embeddings, and turn the raw data or the document into a feature vector. So for example, if a document contains a user's activity and spending data, we might generate a vector like activity score and spend score, right? So in step four, right after transformation, we store these feature vectors in a dedicated container, which acts as our feature store. This ensures like the models or the APIs can quickly access the latest ready to use data whenever they need. And finally, when your application or model needs to make the real-time decisions, whether it's recommendation content or detecting a fraud or personalizing an experience, it simply queries Cosmos DB for a most feature vector for a given user, right? It's as easy as asking what's the latest profile for user 123 and getting an immediate up-to-date answer. So there are like several other optional add-ons we can implement that will enhance the overall functionality. Like we can add Azure Monitor to watch the pipeline health. We can implement log feature metrics. We can also add another Cosmos DB multi-region writes for faster feature availability. Okay, now let's talk about monitoring, right? Because once you build these pipelines, you need visibility into how they are performing in real time. So, why do we, first of all, let's ask the question like, why do we need a custom monitoring dashboard, right? Since AI pipelines are not just one step, they involve multiple moving parts, uh, from data ingestion to feature stores, from model inference to outputs. A custom dashboard helps us to visualize everything in one place, like things like a real-time status of data processing, latency across the different components, RU consumptions inside Cosmos DB, or error rates in Azure Functions. So all these having all this in one place makes it easier for to spot any bottlenecks quickly. Let us also go through the architecture, like how does this dashboard come together? And the answer to this question is it's built in layers, right? So the layers can be like they're like first set of layer is a data collection layer where we use Azure Monitor, application insights, and Azure Log Analytics to gather all the metrics. And then for Cosmos DB specifically, Azure Diagnostics gives us detailed telemetry on RU usage and latency. Next, the aggregation layer, all the raw telemetry that needs to be aggregated and made sense of, right? For example, we use Azure Data Explorer or Azure Monitor workbooks to process and organize these metrics. And finally, we have a visualization layer where we bring those metrics into life using dashboards. Either we can use either a Power BI or Azure Monitor workbooks. And if you prefer more customizable visuals, you can even integrate Grafana with Azure Monitor and your data source as your data source. So then comes setting up the alerts, right? Of course, having dashboards are great, but ultimately we need to also need to be proactive and set up the alerts. That's where there are many ways we can set these alerts. We can set up alerts for Cosmos DB throttling events or functional errors which are above 1%, or drops in a predictive volume, or query latency across different defined thresholds, or sudden spikes in the RU usage, right? So these alerts can be fine-tuned based on your specific project and needs. So in short, the monitoring dashboards become more mission critical for AI workloads, helping you to stay on top of your performance, reliability, and efficiency in real time. Next, let's take a moment to look at how multi-region architecture helps us to scale globally while keeping performance and consistency in check. So first, let's ask why multi-region, right? So if you look at the inference workloads, which are often global, users might be interacting from different parts of the world. So multi-region deployments ensures like low latency responses everywhere without sacrificing on consistency. So let's also analyze on how this architecture works. So we use multiple write regions in Cosmos DB. This allows like writes to happen in different geographical locations and reducing the latency for regional data updates. We also configure automatic failover. So if one region has an issue, another region takes over without any impact, right? So this setup ensures like fast reads close to the user without overloading write regions. So now, when you have multiple write regions, conflicts can happen. Cosmos DB conflicts resolution policies can help manage these scenarios. But for AI specific data types like embeddings or feature vectors, we go one step further. where we use custom merge handlers to combine conflicting writes. So this ensures that the data remains accurate and reliable all the time for the downstream. So now let's talk about how we can optimize costs across AI workloads while still maintaining the performance and scalability. So first, let's start with understanding workload patterns. We look at historical usage to decide the best throughput like provisioning model. For batch training jobs that run on predictive schedules, programmatic scaling works well. Here we can scale up workloads during training windows and then scale down when you're done with those jobs, right? On the other hand, inference workloads are often unpredictable, meaning for these the auto scale provisioning helps adjust the capacity dynamically, so we only pay for what we need. Next, we look at the container consolidation strategy. By consolidating related data sets like metadata into a shared containers, we can take advantage of throughput sharing. This reduces the total RU consumption compared to the provisioning multiple like separate containers for smaller workloads. Next, we deal with index optimization. Indexing can quietly become a big cost driver if we are not careful. For large objects like embeddings or raw feature data, we redefine indexing policies to exclude the properties that are not queried. Um, Targeted indexing can significantly reduce the RU consumption for write operations. And finally, we use time to live implementations policies for short lived or transient data. This not only keeps the database lean, but also avoids unnecessary delete operations. So by combining smart scaling, container design, and indexing strategies and automatic cleanup, we can manage costs efficiently and effectively. So without, of course, compromising on performance and flexibility. Thank you. I'd like to thank Azure Cosmos DB for giving me this wonderful opportunity to present on this particular topic. Thank you. Thanks, everyone.